So this won't take long. If one of your friends is at the college presentation, make sure they see your notes where you talk to them about this. Even better, you teach them this, because there are 3 test questions in the next 10 minutes. So we don't spend a lot of time in this chapter about colligative properties because somebody up top said we didn't have to, so we're not gonna. But colligative properties basically are things that change depending upon how much impurity you put in your solution. Okay? So we all use this if we drive because you put water in your radiator and it flows through the engine, and it flows through the engine to keep your engine from melting. But as the heat goes into the water to keep your engine cool, that water gets hot. And if it got to 100 degrees, it would boil. So to keep the water from boiling, we add an impurity. The impurity we add is usually ethylene glycol or propylene glycol, and that raises the boiling temperature up. So a colligative property is anything that depends upon the amount of solute dissolved in a solution. So a colligative property is something that depends upon amount. Colligative literally means how much you have. So a colligative property is something that changes depending upon how much impurity or how much solute you've added to your solution. Signed script. That's what happens. Doctors and teachers, their signatures. Okay, so the physical property is actually what changes. So we call this freezing point depression, pushing down freezing points, or boiling point elevation. When you add your impurities to your water, it drives down the freezing point and drives up the boiling point. Some people still call this antifreeze because they're from the north. If you live in Wisconsin, this is antifreeze. If you live in Arizona, it's coolant. Here, coolant. It's very strange, or it'd be very weird if our cars froze up. But in the north, they need the coolant not to freeze, so they call it antifreeze. Here, we want the coolant not to boil, so we call it coolant. But both things happen. The more solute you have, the higher your boiling point, and the lower your freezing point. Usually we use about a 50-50 ratio. Basically, that's as much solute as you can add. If half your solution is ethylene glycol or propylene glycol, you've driven your boiling point as high as it will go, and driven your freezing point as low as it will go. This is the formula that you don't have to use. It's delta T equals the constant times molality, but you don't have to do that anymore. So there you go. All you need to know is the more impurities you have, the further the property is going to change. The higher your boiling point is going to be, the lower your freezing point is going to be. Okay. Does that make sense?
Yeah.
Did I go too fast? Give me a thumbs up if you're ready to move on. Moving on. Okay. So, osmosis. You know about osmosis. You learned about osmosis in like 4th grade. And then you learned about it again in biology. What is osmosis?
Water.
Exactly. It's water passing through a membrane. Well done. Yeah. It's water passing through a membrane. I have a reverse osmosis water purifier under my sink, so the drinking water tastes better than the tap water. It pushes water through a membrane. Well, that's what osmosis is. It's pushing water through a membrane. Specifically, it's the travel of a solvent from an area of low concentration to an area of high concentration. Or you can think of it as the travel of a solvent from an area of high purity to low purity. Pretend that's a square. So osmosis is the natural travel of a solvent from an area of low concentration to an area of high concentration. You can also think of this as an area as traveling from an area of higher purity to an area of lower purity. So I've got 2 samples of solution, and this is my membrane. There's a membrane right there. It's what we call a semi-permeable membrane. Semi-permeable means some things go through. Semi-permeable membrane. Do you believe, so without blurting it out, do you believe the solvent's going to go that way? Or do you believe the solvent is going to go that way? So chat with your neighbor for a minute or two and figure out what direction you think the solvent's going to go. Is it going to go blue to the right or green to the left? So chat with your neighbor and figure out what direction the solvent will go. In reality, it's going to go both ways, but one of them is going to be dominant.
They're going to go both ways until they equal, and then they're going to explode.
That's right. So they are going to go both ways, but one is going to be going one direction faster than the other one. How does he snap with that constant? It's almost like slippery. You really are to snap with that.
You think about it, he's like, it's nice so well. It's impossible to snap your
All right. With a show of hands, as in like that or that, do you believe that the solvent is going to travel this direction or this direction? So, interesting. It's about 50-50. Okay. Now, this has 4 impurities. So this is purer, and this is less pure. Solvent travels from an area of high purity to low purity. Does that change your answer? Yeah. Okay, so which direction is it going to go? Yeah, it's going to go that way. So if this has 4 molecules of impurity, and this has 6 molecules of impurity, the solvent's going to travel across, because what the solvent wants to do is create a situation where all it sees is the same purity in both sides. That's what it wants to see. It wants to kind of equalize the purity. So solvents will move from an area of high purity to an area of low purity to kind of equalize things. That's what it wants. So this is kind of fun. This is kind of thing you don't get to do anymore because people are freaked out about blood, even pig's blood. But back when I was growing up, you would take a dropper full of pig's blood, and you look at it under a microscope, and you put the red blood cell into pure water, and the pure water would go into the red blood cell until the red blood cell pops. Because the solvent would keep going in and in, high purity to low purity, and keep going in and in and in until the red blood cell just popped. You can try it if you have a microscope, or you just steal one from biology. You can take it home and stab your finger and put a little drop into pure water, and you can look at it and watch the red blood cells do their thing. And now we do also the same thing with brine. Brine is a saltwater solution. You put some red blood cells in brine, and then the blood cell is the high purity, the brine is the low purity, and the blood cell would shrivel up like a raisin. There's YouTube videos on it if you're really interested in that kind of thing. So what do we use this for? We use it to make pickles. Pickles! Yay, pickles. We use it to make pickles. So in the pickle, see, you go to the pickle tree and get pickles? Yeah. Okay. You put the cucumber in a solution of brine, and the cucumber is the high purity, and the brine is the low purity, so the water goes out of the cucumber. That's how they make pickles. Some of you are like, I have no idea. Wait, that's how they make pickles.
So why don't we call them osmosis?
Yeah, like, well, same reason we don't call raisins grapes, like old grapes. Like, so yeah, a pickle is really a cucumber raisin. Okay, questions about this stuff? Moving on. Oh, this is also why you want to store carrots and celery and stuff in water. because the water will go up through the celery or up into the carrots and keep them firm. Last thing. There are two special ions that you need to know about. Two special ions you need to know about. You've actually seen them before, but I'm going to highlight them because they're important, and then there's one concept we talk about. The H plus ion, also the H3O plus ion, is the special ion involved for acidity. We're talking about acids and bases later on. It's the ion involved in acidity, and it's called hydronium. The H plus or the H3O plus is called hydronium. It's the ion involved in acidity. You've actually seen before because we talked about it when we did polyatomic ions and nomenclature, is hydroxide. The OH minus ion is hydroxide. Hydroxide is responsible for basicity. It's the thing that makes a base. It was the preponderance of hydroxide ions that made our solution so dangerous yesterday in the gold penny lab. And lastly, we talked about electrolytes earlier in the unit. We're almost done. You can test this tomorrow. We talked about electrolytes. Something can be a non-electrolyte when there's no ions, and it has to have ions to be an electrolyte. But one thing we kind of briefly mentioned in the lab is the difference between strong electrolytes and weak electrolytes. A strong electrolyte disassociates completely. 1,000 molecules in, 1,000 of each ion out. A weak electrolyte disassociates only partially. 1,000 molecules in, 100 of each ion out. So a weak electrolyte disassociates only partially. A strong electrolyte disassociates completely.